Hey, welcome, Erez and Alexine, Alexis and Susanna and Stefani and Diego, Antonio, Rigny, Adam, and Khan. Thanks for coming. So let's jump right to the quiz and take a look at how we can solve those problems. Okay, so here's the quiz. And the first question is, let f of xy equal 7 plus y squared minus 4y over x. And we want to find del squared f over del x del y. Okay, so I have a kind of a trick question for you. Does that mean, do we need to take the derivative with respect to x first or respect to y first?
To x first.
Okay. Yeah, I like Adam's answer anyway. It's a trick question. The answer is either way. Okay, you get to choose because there's nothing wrong with this. It's just a regular old function. Again, you got to really work hard to come up with one where it matters. I mean, really work hard. It's going to have all kinds of piecewise stuff, and you've never seen anything like it. So basically, you can always choose x first or y first. And I'm going to look at this, and I'm going to say, which do you think is easier to take a derivative of first? Yeah, x, because then that y squared goes away. Isn't that nice? Okay, so notice del f over del x is equal to, well, the 7, derivative of 7 is 0. What's the derivative of y squared with respect to x?
0.
Also 0. And then I like to rethink this negative minus 4y over x as minus 4yx to the negative 1. It's a little easier to think of the derivative. Derivative of x to negative 1 is negative x to the negative 2. And the 4y is a constant. So we get negative negative, which is positive, 4y x to the negative 2. Any questions on del f over del x? Okay, now we need to finish it off. You write del squared f over del x del y. So I just took the derivative with respect to x. Now what do I have to do?
Take it to y.
Take it to y. Okay, and again, you need to focus on what are the constants and what's your variable. The variable is y. So that means this whole x to the negative 2 is one big fat constant. 4 is a constant. So this is just a constant times y. And the derivative of a constant times y is a constant. So I just write the constant, which is just 4x to the negative 2. Any questions at all on question 1?
Yeah, I have a question.
Mm-hmm.
So in the homework, it was kind of like having you put it in like different boxes where like when you'd find, is this the same thing as finding f of xy?
My guess is what you're thinking is the answer is yes. What you're saying is wrong.
Yeah, not of like.
Yeah, because f of xy is just 7 plus y squared minus 4y over x, because that's what it says.
No, I know what you mean.
F sub xy, right?
Yeah, exactly.
Yeah. So f
but basically,
yeah, it's exactly the same as f sub xy.
Yeah. So they ask you to find like f sub x and f sub y, and then how the answers were turning it out, it looked like you took the derivative, like the different part of both those equations, and put them together. But I guess like if you would do that here, you would have had the f sub y would have been 2y. But so there's no 2y in the answer?
No, there's no 2y in the answer because this is a second order partial derivative, and one of the derivatives with respect to x, y squared is a constant. Derivative of a constant is always 0.
Okay, so you can do it like based off of 1 and then just take the second.
I'm not sure what you mean based off 1.
Like just off of x, and then you take y off of what you found of x.
I mean,
I understand this way. I understand.
Really, you have to take a partial respect of one of them, one of the variables. If you have a mix, this is called mixed partial derivatives, You have to take a partial derivative with respect to x and then a partial derivative with respect to y of what you got after taking the partial derivative with respect to x.
Okay, perfect.
Okay.
Thank you.
And as I mentioned, the big theorem was that if, I don't know, you were in a y mood first, you could take the derivative with respect to y first and then take the derivative with respect to x, and you will get the same answer. You'll still get 4x to the negative 2. And that's the theorem. The theorem says you get the same thing. Does that make sense?
Yeah, thank you.
Yeah. Okay. Other questions on this? Okay, so let's look at the next one. The next is consider the contour diagram below that shows f of xy. Approximate A, f sub x of 0, 1, and B, f sub y of 0, 1. All right, so I'm gonna just point to 0, 1. Hopefully you all know how to plot a point, and that's right up there. And we want f sub x of 0, 1. All right, and we have, this contour diagram. How do I approximate an f sub x of 0, 1? And it's pretty easy in this case. This is the easiest of the two parts. Yeah, you move a little bit to the right, just a tiny step. And the key here is that when you move to the right, you're actually walking along the contour diagram. Do you see that? Along the contour line, or the contour curve, I guess. So if you're walking along the contour curve, what does that tell you how much you've gone up or down? Yeah, you haven't at all. So f sub x of 0, 1 is just 0 because we're walking along the contour curve or line. So let's write that down.
Larry, I actually have a question about that.
Mm-hmm.
So I understand the concept, but I feel like in terms of even in the smallest increment you could think of, technically that line is only at one spot though. As soon as you move away from it, aren't you technically then going downhill in a way, or in this case it would be uphill?
Okay. So
if you were walking along that curve, then yeah, perfectly, it's 0 the whole time. But as soon as you take one step, don't you step away from that line?
All right. So now you got to remember, what's the name of this class?
Calculus.
Calculus. And what calculus is all about is really looking at limits. So now when I say you're walking along a line, let me rephrase it. An amoeba is walking along this curve, okay? And what's that amoeba gonna feel?
I still feel like even in the smallest increment, like I said, there's only one spot technically that's on that line. I mean, I think I'm just arguing with you, but I feel like
taking the limit, but we're taking the limit as the delta x goes to 0.
Right.
And that's why I said the amoeba. Now get it smaller than amoeba, or what, you know what I mean? So the point is we're taking a limit. So we're zooming and zooming and zooming and zooming. And the more you zoom, the more you'll see that this line doesn't look like what we're looking at. It's just going to be a horizontal line at that point if you zoom in enough. Does that make sense?
Yeah.
And the limit of
when you put it that way, I feel like that makes sense. But
yeah. And I
feel like you don't do that though. You don't always place a tangent line everywhere though, do you?
Oh, if you want to find the derivative, you're always zooming into, you know what I mean? That's a limit. The derivative is defined as a limit. So yes, you are. No matter where you're looking at, whatever derivative you're looking at, you're always zooming in. Do you see that?
Yeah. Yeah. Okay. All right.
Right. And the slope of this hill will be 0 zoomed in. Does that make sense?
Yeah.
Yeah. If you zoom out, that's different. But zooming out is not calculus. Zooming in is calculus. And that's the big thing. And it's an infinite amount of zooming in. That helps some?
Yeah, I suppose so. Because, yeah, that helps. Because I was going to say either way in the other direction, if you went in the Y direction, if you were amoeba, technically the line would be bigger than the amoeba. But in that's just splitting hairs. I see what you're saying, though. It makes sense.
Right, but the point is it would still be a slope down, right? You'd only go a tiny bit down, but you're only walking a tiny bit. And if you take the ratio of the amount down versus the amount, and I'll get to going down in a minute or up.
Oh, okay. Yeah, I see that.
It's all about ratio, because remember, derivatives are ratios, right? It's the change in the function divided by the change in the variable. Do you see?
Yeah.
And the change in the function divided by the change in x is 0 as the limit goes to 0, as the change in x goes to 0. Does that make sense?
Yeah.
Okay. And you can imagine, you know, if you're standing on some kind of sloped plane or sloped mountain, then, you know, there is a downward slope that you're feeling, right? But if you go to the left or right, if you were looking down, then the derivative would be 0 because it's not downward. Does that make sense?
Yeah, I mean,
even if
no, I see what you're saying. It's
yeah, maybe a mile away it starts going up, but where you're standing, it's not. Do you see?
Right. Right. No, the ratios is really where they really drove home. I understand.
Yeah. Yeah. And calculus, derivatives are all about ratios, right? Because slope is rise over run. And that's the key. Okay. Any other questions on this? It's good questions, though. Very good questions. Okay. So f sub x of 0, 1 is equal to 0. Let me just write y. That way, you know, if you explain yourself, that way you can get partial credit if you make a little mistake. Since the x direction is in the direction of the tangent line to the contour line. Okay, now we need to do f sub y. Okay, and if you're going to do f sub y, still at 0, 1, still at this point. So now you're taking a step north. Does that make sense? So now we got to say, if you take a step north, then first thing, are you going upwards or are you going downwards? And remember, it's true up and down, not north, south, up and down. But if you go north, are you going to gain or lose elevation?
Gain.
Okay, so take a look at this line. This has a -1, and the next line north has a -2.
Oh, well, you're going downhill.
Yeah, so we're going downhill. That means we're going to lose elevation, right? So we're going to lose elevation. That means, for one thing for sure, is that the partial derivative is positive or negative. What do you think? With respect to y? Yeah, it'll be negative because downhill is negative, right? Slope down means negative partial derivative. Okay, so we know it's negative. Note, by the way, now we can look at the units. From 1 to 2, that's like way more than a contour line, right? So if you just walk to the next contour line, you've walked like less than a half of a unit north, but you've gone down a whole unit in elevation. Is that clear? Any questions on that? So again, you want to think of it as rise or run. So the rise now is your elevation change. And that would be like a whole unit down, -1. How much is the run? If you go from here to here, say. Let's call that the 1 step. About how much is that? Yeah, maybe 0.4. Okay. And remember, the derivative is the rise of a run, okay, approximately, of what we're visualizing. So that means we are rising -1, and we're running 0.4. So let's write that out. So f sub y of 0, 1 is about equal to, I'll write equal because I Don't want to put the about equal to symbol. And remember, we went down 1 and we went north about 0.4. Any questions on that? And if you feel like that, feel like it, that's -1 over 0.4 is -1 over 4 times 10, which is about 2.5. If I'm doing my head right. And there's our partial derivatives back to y. Okay. If you did 2.3, I mean, like I said, you can't tell exactly what it is from this picture just by looking, but we can estimate it. And the key again is kind of showing this rise or run idea. Any questions on reading the contour diagram and equating it with the derivative?
Wait, can you go back to show FY to the map? Yeah, thank you.
Yeah, so again, it's a rise or run. We're rising. That's not how far you're going up y, by the way. That's how far you're going up on f, the -1 to -2. So we're rising -1 and we're running by 0.4, about. Any questions on this?
Yeah, I think I just messed up because I just followed the green contour to the number it leads to. Because I think in homework it was sort of like that. Because there were some like funky estimations yesterday. It was like 160 minus 120 divided by like 12 minus 9 or.
Yeah, the numbers won't mean anything to me because remember they're randomized, so everyone gets different.
Yeah.
But
I was going off of that pattern when I was doing this problem, but I think I understood what you were doing.
Yeah, you want to think about rise over run because that's what a derivative is. And again, you got to put your mind on rise, meaning the change in the function divided by change in the variable is what we want to look at. Any questions at all on reading this? Okay, any questions on the quiz at all? The whole quiz? Okay, if there's no questions on the quiz, let's pop into our plan of the day. And that is we're on Q&A time. So are there questions on homework or on anything else that's coming up? Anything you've been working on calculus-wise? Now that we're really in calculus instead of analytic geometry? Any questions? Questions about today's lesson? About today's lesson, but I haven't gotten to today's lesson yet. We'll get there. Unless it's structure or something. Oh, today's homework. Yeah, homework's different than the lesson. The lesson is what you're looking at right now. Yeah, if you want to wait until after, that's fine too. Because I always have office hours after class. If you want to do that, and I can explain there too. But if there's no other questions, I can move on. So I have a question for you. It's kind of an interesting question. If you go back around, I don't know, 1,500 years ago or so, and you talk to a sailor, okay, and you ask them, what's the shape of the earth? What would they tell you?
Probably flat.
It's flat, okay? Now, you know it's not. I hope you know, by the way. I hope you're not one of those weird people. But here's the more important question. Why did they think it was flat?
Because they were sailing at sea, and it looks kind of flat if you're on the ocean.
Yeah, so
you
if you
can't see the
wave,
curvature, like as if you were in a plane, you could see the curvature, but there's no planes.
Yeah, 1,500 years ago, they weren't in planes.
Yeah.
That's for sure. They were in boats. Okay.
So it looks straight. It looks like directional.
Yeah, yeah. And I'm not talking about waves. Waves aren't the issue. But I'm talking about just, you know, on a calm day, then, and you look out in any direction, it's going to feel like the earth is flat. Do you agree? Okay. Again, but I'm not trying to tell you the earth is flat, but I want you to realize the difference between calculus and a universal viewpoint of everything. Okay. A universal viewpoint, that means you can go out and, you know, and do what those people in the ISS do. They go out and they look and it's obvious it's not flat. Okay. It's obvious it's a sphere. But then when you go out on a boat on a calm day, it looks flat. And it turns out it's not just the earth. That's pretty much true of most objects and anything that's got anything smooth. Okay, is that if you zoom in, it looks flat. So let me just give you an idea. So by the way, take a look at what we're looking at now. Does that look flat to you, this surface?
Absolutely not.
All right. On the other hand, I don't know, let's zoom in. And all I'm doing is zooming in. What if I asked you again about this surface? It's the same surface. Maybe I'll zoom in a couple more times. Would you change your mind if I said, does this look flat?
If you show me this first, yes.
Yeah, that's all we've got. That's all you get to see. Okay, and you look at it, and what would you describe this as? If I said, what shape is this surface, what would you tell me?
Square.
Square, but in particular, a plane, right? Because I know this is one of the problems with computers is that, you know, they have to make it a square, but it's a plane. Any questions on that? Okay, now maybe one question you might have is this special? You know, did I choose this one because this is the one that looks like a plane? Does that make sense? And of course, now I zoomed out and everything changed. So maybe I can change it to a different shape. I don't know. I'll throw something in there. I'll just make something up. How about x times cosine of y plus, how about e to the, how about negative 2x plus y? Oops. Negative 2x plus y. I'll just throw something out like that. Is it flat? Is it a plane? Would you call that a plane? Okay, but now let's be the sailor. So now I'm going to zoom in, and I'm just going to hit the zoom in button. I think I need to change, if I'm zooming in that much, I need to change Y. Yeah, this one, I need to go from 0.99 to 1.01. I think we'll do it. Yeah, this might have a problem because it's not able to show it unless you change the center. I'm not sure. Is it that one? Nope. Sorry about that. This might not have been the best example because it's not easy to change centers. So I change the center of what it shows. But yeah, let me do -1. Let's try this again. Yeah, if we don't have it go through 0, 0, the program's a little harder to work it with. So how about sine of x squared minus y minus 1 plus e to the x minus 3y. That should work. All right, again, hopefully you notice this doesn't look flat at all. But if I zoom in, and then all of a sudden, what does it look like?
A plane now.
Looks like a plane. Will that always work?
Not really.
When won't it work?
When you have a function that doesn't exist.
Yeah, when it's not continuous, or even better, what if we did, it could even be continuous. But how about, I think this will work, absolute value of x plus y. So there's the absolute value of x plus y. And let's zoom in. Whoa, what just happened? There we go. And what do you notice? If I zoom in a bunch, what does it look like? Does it look like a plane?
Not really.
No, it still doesn't look like a plane. What do you think if I zoomed in 100 times more, would it look like a plane? Still wouldn't. What's going on here? It's continuous.
The absolute value.
Yeah, but it's continuous. So what's the issue? It's not that it's not continuous.
It's infinite.
It's not infinite, actually. Near the origin, it's not infinite at all. Yeah, it's not differentiable. So it turns out the absolute value, and you got that in first quarter, is the absolute value function is a classic function that is continuous but not differentiable. Do you remember that at one point in your life? So what we want to do, at least mostly in this class, is we're going to focus on functions that are differentiable for now. And if you have a function that's differentiable, then if you zoom in at any point, it'll look like a plane. Any questions on this idea? All right, so now we're ready to give the big definition. And it's kind of a two-part definition. So here's the parts. Okay, let z equal f of xy, okay, be a function. And let's suppose the partial derivatives are defined at the point x naught, y naught. Okay, then the tangent plane at a point x naught, y naught has this equation. And the equation is f sub x of x naught, y naught, so the partial derivative of f with respect to x, evaluated at the point, comma f sub y of x naught, y naught, comma -1 as a vector. I need, that needs the vector notation, dotted with x minus x naught, comma y minus y naught, comma z minus z naught is equal to 0. Okay, so I want to look at this a little deeper. If you have the dot product of two vectors equals 0, what do you know about those two vectors? What do we call them by definition? Starts with an O. Yeah, orthogonal. Okay. So what this says is that this interesting vector, f sub x, f sub y, and comma -1, is orthogonal to x minus x naught, y minus y naught, and z minus z naught as a vector. Okay. Now, we've seen this before. When you have x minus x naught, y minus y naught, z minus z naught, geometrically, what are we talking about? So this piece, this vector, geometrically, what does that represent? We did this a couple weeks ago. Wasn't a slope. The key is we're talking about a plane. And what does that represent for the plane? Yeah, it was a vector on the plane. Do you remember that? So this x minus x naught, y minus y naught, z minus z naught is any vector on the plane. Now, what about the vector that you dotted with and got 0? What do we call that vector? Again, you know, a couple weeks ago, we didn't have f sub x, f sub y. But when we had an equation of a plane, what was that first vector we dotted with called? Starts with an n. Yeah, that was the normal vector. Okay. So this is telling us that the normal vector to the plane is the partial derivatives comma -1. Any questions on that idea? You can also, you know, work it out, take the dot product, and notice you'll get an f sub x times x minus x naught. You'll get an f sub y times y minus y naught. And you'll get a -1 times z minus z naught. So if we do a little basic algebra, very basic, you end up with z equals f of x naught y naught, okay, which by the way is the same as z naught. Okay, that's just z naught is kind of shorthand for f of x naught y naught. And then plus f sub x of x naught y naught times x minus x naught plus f sub y of x naught y naught times y minus y naught. And that's just simple solving. You guys can all do that, and, you know, without an issue, I hope. Okay, the tangent plane is the collection of all possible tangent lines at the point for curves that lie on the surface. Okay, so that's some geometry about what the tangent plane is. So let's go back over here and let's do the original one because we want something differentiable. Okay, and even let me pop in, how about an extra? I think that'll make it better. No, that didn't work. How about plus 2x? There we go. So notice at the origin, because that's what we're kind of looking at, then there's a tangent plane that I can zoom in on. And there's our tangent plane. We can see it. Let's zoom back out. So if we take a curve that goes through the origin, maybe something like that, and we take the tangent line to that curve, that tangent line will be on the tangent plane. And if I choose a different curve, maybe over here, like that, then if I take the tangent line to that curve at the point, then we'll still be on the tangent plane. So the tangent plane can also be looked at as the collection of all possible tangent lines to curves that go through the point but stay on the surface. Anyone lost on this geometry? Any questions on this? Okay, so there's our definition. And one nice thing, does this look very hard to actually do by hand? What do you think? Either the equation or the same equation. Yeah, this isn't that bad. Okay, there's no trick here. You just got to remember, and I like to remember it geometrically. Okay, later, not today, we're going to have a word for this special vector, this first vector, but not today, so I'm going to hold off on it. But this vector, first thing is that this is the normal vector of the tangent plane. So that's nice and important. And we'll talk about why this works also. Any questions so far? So let's do an example. And the examples, again, they're not that deep. There's nothing special about them. But we should do an example, otherwise you may feel uncomfortable. So I don't know, how about let f of xy equal, how about 2x squared y minus y squared plus 4x. Find the equation of the tangent line to this surface at the point, how about -1, 2. Any questions on the question? Timmy does. Any question on the question? All right, so what's my first step, by the way? And there's a couple choices for first step.
Should you plug in?
Yeah, let's plug in. Okay. And by the way, someone else said derivatives. Remember I told you there are a couple choices, so those are 2 choices. So we're going to do both. So I'm going to plug in first. Let's do new equation, f of -1, 2. Come on. Let me just plug in. So let's do it. -1 squared is 1. 1 times 2 times 2 is 4. Minus, and then 2 times 2 is 4. And then plus 4 times -1, which means -4. A lot of 4s here. And that equals -4. Any questions at all on plugging it? Okay, the next thing I need to do, I need to find the partial derivatives. Okay, so I need to find the partial derivatives evaluated at the point. So let's first find the partial derivatives back to x. F sub x is equal to, and let's see if you can tell me what f sub x is. Not supposed to be that hard. Yeah, it's 4xy plus 4. And now I want f sub x at -1, 2. And what do we get? Just coincidentally, I literally made this one up. I didn't expect to see same numbers.
-4.
-4 again. I hope the other one's not. Okay, then we need f sub y. What's f sub y? So what's f sub y? F is 2x squared y minus y squared plus 4x. Yeah, it's 2x squared minus 2y. So f sub y is equal to 2x squared minus 2y. And now f sub y of negative 1 comma 2 is equal to, now you just plug in negative 1, 2. So if x is negative 1, y is 2, you get 2 times 1 is 2, minus 4 is negative 2. If I did my arithmetic right. Any questions on that? Okay, now ready to put it together. I'm going to write in vector form. So we have f sub x of x naught, y naught, and that was negative 4, comma, and then f sub y of x naught, y naught, and that was negative 2, comma, negative 1, dotted with and then we have f sub y, then we have x minus x naught. And actually we know x naught, so it's x minus x naught was negative 1, so x plus 1, comma, y minus y naught, and that's y minus 2, comma, and then z minus z naught, so that's z minus negative 4 or plus 4 equals 0. Any questions on this example? Any questions?
Wait, how did you get z naught?
Z naught is just f of x naught, y naught.
Oh, okay.
Yeah, I wrote it this way because it just looks prettier. But you can write it as f of x naught, y naught if you want, but it's just messier. I think it looks prettier to say z minus z naught, doesn't it? So then finally, let's do that dot product. I think it's worth it. And I'm going to work it out. We get negative 4x minus 4. And then we have minus 2y plus 4. And then we have a negative z minus 4 equals 0. Okay, I'm going to bring the z over and then switch. So you get z equals, and we get negative 4x minus 2y. And then when you add this up, you get minus 4. Any questions on how this works? Any questions on this example? It's a little messy, but it's not that hard, is it? Sometimes you can end up with messy fractions, but other than that, it's no big deal. Okay, so why is this true? That's the next question. Okay, first thing is we know that x naught, y naught, z naught should be on the tangent plane. That's obvious, I hope, right? It's just like the tangent line at a point contains the point. Well, the tangent plane at a point should contain the plane. But why is this here, f sub x, f sub y, comma negative 1, why is that a normal vector? How do you find a normal vector to a plane? How do you find a normal vector to a plane? Using points? You could use points, but in particular, you take two vectors on a plane, and what do you do with them?
Find the intersection?
No, not the intersection. We did this, but it's been a couple weeks already. Yeah, there we go. Use the cross product. So we know that the normal vector is a cross product of two vectors on the plane. Any questions on that? But again, the tangent plane is the collection of all possible tangent lines at the point for curves on that line on the surface. But there's two special tangent lines. The two special tangent lines are if you cut it parallel to the x-axis, you get a curve, and you can take the tangent line to that curve, and the slope of that will be f sub x. And similarly, if you take the curve that is parallel to the y-axis and take the slope of that, that'll be f sub y. Any questions on that? Okay, so we know that we get that f sub x and f sub y. Any questions on that idea? Okay, so that's kind of the idea. I don't think I'm going to do the full proof, but to let you know, what you do is you find the equation of the tangent line to the curve that is parallel to the x-axis, and its slope will be f sub x. And it's going to go through the point x naught, y naught, z naught, okay? And its slope will be f sub x. Okay, that's the slope in the x direction. Okay, and if you take the cross product of the one with the x and one with the y, you can trust me or read the book, you end up with this normal vector right here. Any questions on that kind of idea? Okay, again, if I prove everything, then I don't get to do any examples. And what I found, most people like to see examples. Am I right? If you want to look at proofs of everything, then you take that 2 more years of math and you'll take full proofs classes. But for us, I just kind of hint at proofs, or I do basic proofs. That one's a little messier. Okay, so here comes the next definition. There's not much to say about this one. So let me read it and then I'll talk about it. And that is, let z equal f of x, y be a function with defined partial derivatives at the point x naught, y naught. Then the linear approximation is given by L of xy equals z naught plus f sub x of x naught, y naught times x minus x naught plus f sub y of x naught, y naught times y minus y naught. What is this doing? When we're talking about linear approximation, what are we talking about here? Kind of the idea of this. It looks like the dot product. Yeah. But what does it look like that we've seen very recently? Okay, partial derivative business equation. What I'm hoping you notice is this is just a tangent plane. Let me scroll up a bit to remind you. Isn't this a tangent plane? F of x naught, y naught, and then you take the fx times x minus x naught, fy times y minus y naught. That's exactly what this is. It's the same equation. So if you remember, the best linear approximation for a curve was a tangent line, right? Well, the best linear approximation to a surface will be the tangent plane. Any questions on that idea? That's all this is. This just says the tangent plane is your best linear approximation to the function. Okay, does that mean it's a good approximation long-term? Like if you're very far from the point? No, no. And in fact, for example, on Earth, if we go 3 light years away from a point on Earth and use a tangent plane approximation, you're going to be on some star far away. On the other hand, if you travel for 3 light years along, in a boat in the Pacific Ocean or something, you're not going to be in some other star. Does that make sense? You're going to still be on Earth. Okay, so if you don't travel far, it's a good approximation. But if you travel far, it's a terrible approximation. Any questions on that idea? And that was the same as when we had one variable. All right. Why do you think this is used? In the real world? It's 3D, but that's not the reason why it's used. Could use it in 4D also, by the way, although this just is 3, but it extends to 4. Let me give you an example, and then I'll talk about kind of why you'd want to use it. Let's suppose f of xy. Oops, let's go to so let's suppose f of xy was equal to cosine of x minus y plus the sine of x. And the question is, what is an approximation, a linear approximation for f of 0.1 comma negative 0.2, somewhere close to the origin. Okay. Any questions on the idea? Okay, what do we have to find?
The derivative.
Yeah, we got to find derivatives, right? We're in calculus now. Everything's going to be derivatives. So let's go find them. They're not hard. F sub x and we're plugging in 0, 0, because that's going to be our x naught, y naught, because that's the nice number to be able to plug in. Okay. Well, what is f sub x? And I could do this in my head. I get negative the sine of x minus y. If I plug in 0, 0, that just gives me 0. And then I get plus the cosine of x. Cosine of 0 is 1. What's f sub y? Of 0, 0. Well, I take the derivatives back to y, and that is going to be positive the sine of x minus y. Plug in 0, 0, you get 0. Plus 0, and that just gives me 0. Any questions on that so far? Okay, we also need to find f of 0, 0. And f of 0, 0 is 1, because cosine of 0 is 1 plus sine of 0, which is 0. So 1 plus 0 is 1. Any questions so far? So now what I can say is that f of 0.1 comma negative 0.2 is going to be equal to, I just plug in, okay, and z naught was 1 plus, and then we had f sub x was 1 times x, and x is 0.1 minus x naught, which was 0, and then plus, and then we have f sub y, which is 0. I could ignore the rest, but still I'll write it in, times y minus y naught, which is negative 0.2 minus y naught, which is 0. And what do you get? Hopefully you can all do this in your head. 1.1. Any questions on that? Okay, now
actually, Larry, I have a question. Is f of x of 0, like would the normal vector be 1, 0, 1? Is that what that is? Like when we found the f of
1,
x,
0,
f of
negative
sub
1.
y.
1, 0, negative 1. So remember in the formula, the third component is negative 1.
It's always negative 1. Z is always negative 1.
Yeah, and we'll understand that in a few days. Or
Okay.
maybe, I mean, it'll be next week. So next week, a few days of
Okay.
Sunday. But yeah, next week, we'll get that next week. Okay. But we're not there yet. And we will get there. Right now, I'm just telling you, trust me. Sound good? All right. So I was able to get a linear approximation or approximation of 1.1 without doing, just in my head, right? I mean, I wrote it down, but I didn't even need a calculator, did I? I didn't do anything fancy, did I? What if I asked you, what is f of 0.1 comma negative 2, period, and you don't get a calculator, and I said, go and find that. Could you do it? Right? You'd plug in, and you get cosine of 0.3 plus a sine of 0.1. And can you tell me what cosine of 0.3 plus a sine of 0.1 is without using a calculator? Okay. Sine, yes. So what's the sine of 0.1? Really? It's not exactly 0.1.
I thought with the sign, the closer it is, like the smaller the margin, you can just use it as is.
Yeah, but if I told you exactly what it is, could you tell me? The answer is no.
Okay, then no.
There's no chance. Yeah. What you just said is what I just did, is you gave me an approximation, a linear approximation. I did it more sophisticated because I used it with a 2-variable function. But what you did was a linear approximation in 1 variable. But the point is, you still didn't give me the number. So the answer is no, you can't just do it in your head. And now, let's say you did have a computer, and let's say you had to calculate 3 million of these with your computer. And let's say you were programming a video game, right? Some kind of game, and it animates and stuff like that, and it needed to do 3 million of these things so that it could do the animation. What's going to be the problem?
The computer might crash.
The computer's going to crash, or it's just going to get slow. Nobody's going to play your game, right? So what you do is when you have to write down or do computations with the computer and speed is important, then you do linear approximations. Any questions on that? Because I'll never tell you have to, do everything in your head and that's just life. No, that's not true. But life is, you have to do linear approximations or the computer goes too slow and nobody wants to play your game or nobody wants to wait 10 minutes to get the answer. So that's the issue. So linear approximations are very important for efficiency. Any questions on that idea? Okay, and what this does is all it's doing is it's saying we're going to ignore the surface. We're just going to use a tangent plane. That's all this is. Okay, so do you remember what it means for a function of one variable to be differentiable? Good old first quarter calculus. What does it mean for a function to be differentiable? Pretty simple. Yeah, so if you use the limit, when you say the limit, if you use the limit definition of the derivative, you actually get a limit and you get a derivative, right? Any questions on that idea? What's the problem with jumping to two variables?
You won't always have both sides to work with.
Both sides?
I mean, it won't always be continuous. It won't.
That might be one variable is not always continuous. It's a bigger issue. And the issue is we don't have a derivative. Yeah, there is no derivative. Right? If I say, what is the derivative of this function I just wrote down? If you could tell me what the derivative is, you're wrong. Because there isn't a derivative, right? We could talk about a partial derivative with respect to x or a partial derivative with respect to y, but that's not the derivative. Those are partial derivatives. Does that make sense? So what we want to do is we want to say, well, what does it mean for a function to be differentiable? So geometrically, to be differentiable, you want to make sure that the tangent line is a really good approximation to the surface. That's basically what you need. You need that tangent line to work. Now that's great geometrically, but that's not really a formal definition. So I want to let you know you might be a little scared when you see it because it's messy, but here's the formal definition of differentiability. So a function f of x, y is called differentiable at a point, x naught, y naught, if there exists a disk around P. So remember when you looked at differentiability, as I saw in the chat box, that meant you had to go from the left and the right and get the same things, right? Well, here there's no left and right, right? Now we're talking in 2 dimensions, but we can talk about a disk. So instead of left and right, we can take a disk around the point such that all points x, y in the disk, f of x, y is equal to the tangent plane, this first bit. Let's see if I can get the first bit. It's not giving me the first bit. Let's see. Oh, well, it won't let me highlight the first bit. But the first bit, the first 3 terms, plus some error. So what it says is that a tangent line is a good approximation to the function. And what does it mean for it to be a good approximation? What it means is if you take the error term and you divide by the square root of x minus x naught squared plus y minus y naught squared. What is the square root of x naught squared plus y minus y naught squared? What is that geometrically? Or in words? That's the r. Yeah, it's the r, or the distance from the point to what you're looking at. Okay, so it's the distance from the point x naught to your xy coordinate. And if we take the limit as that distance approaches 0, then the error divided by that distance will be 0. And remember, the distance goes to 0 If the distance goes to 0, what does E have to go to give you a 0 limit? If this fraction goes to 0, what does that tell you E must go to? Yeah, it must go to 0. And not only must it go to 0, but it's going to have to go to 0 faster than the distance goes to 0. Otherwise, you wouldn't get a limit of 0. So this error not only goes to 0, but goes to 0 quickly. Okay, it is too intense to prove or to really get through why this is what you do. But right now, you can just live with it. Sound good? That here's the definition. Okay, and then I have a big note, and that is that this could be extended to functions of more than 2 variables. So what do you think it would look like with 3 variables, an x, y, and a z, for example? What do you think the only difference is going to be for all of this stuff?
You add a term of like z. It's just you keep increasing the number of terms you have.
Actually, you don't increase the terms. You increase the number of elements in the domain. So in other words, you put a comma z, comma z, comma z. There's one, actually you do add one term right here. You can have an f sub z, but you're also going to have an f of x naught, y naught, z naught. And you're going to have an e of x, y, z. And here you're going to have an e of x, y, z. Here you're going to have an x minus x naught squared, y minus y naught squared, and z minus z naught squared. So you just stick in z's everywhere you want to. And if you were doing 20 variables, you could do that too. It'd be kind of boring. Okay. So I'm just going to write it as a note because I don't think it's worth actually writing it all out because hopefully it's obvious. Is it obvious to you guys what it would look like if it was 3 variables? Nothing really big changes. So differentiability is this definition. Does this definition look easy to use as it's said, as it's read? If you had to prove something was differentiable, what do you think? You'd want to do it or not? Okay. Yeah, I wouldn't. I wouldn't. Okay, so mathematicians are lazy, okay? Or we have our way of being lazy. And lazy means that if there's something we don't want to do, we come up with a theorem that says there's an easier way. And here comes a big theorem. Couple theorems. So the first one is not going to tell us whether it's differentiable, but it's going to go the other way. It's that if f of xy is differentiable at a point P, then f of xy is continuous at the point P. Okay, so differentiability implies continuity. So for example, where is, let's write it out, f of x comma y equals 3x, let's just go x over x squared minus 2x not differentiable. Okay, and we're not quite ready to answer it completely, but at least you can know somewhere where it's not. Where is this not differentiable? Can you give me a value of x? Oh, wait, sorry. I want to go not x. That's a mistake. xy. Otherwise, it's not a function of y. Where is this not differentiable?
0, 0, because it'll be undefined.
Okay, 0, 0 is not differentiable. Anywhere else that's not differentiable? and 2. I think you mean what I'm thinking. You mean 0, 2, hopefully? It's got to have an x and y, yeah. So x equals 0, y equals 2 is still not differentiable. X equals 0, y equals anything is not differentiable, okay? By the way, why can't I just cancel the x's and say it's differentiable? Can I do that? Right, I could factor out an x in the bottom, then cancel the x and say, hey, I get y over x minus 2. So I could say, hey, this is just not differentiable when x is 2. What's wrong with that?
You won't get a denominator.
I don't know what you mean by that. Let's write this out. So we can rewrite this as xy over x times x minus 2, which happens to be equal to y over x minus 2. Okay. Do you agree those are equal? Let me know. Do you agree that those are equal? Okay, if you said yes, you're wrong. They're not equal. Look at the left-hand side and plug in x. Tell me what you get. Plug in x equals 0. What do you get on the left-hand side? You get 0 on the top, 0 on the bottom. That's not 0. 0 over 0 is not 0. On the right-hand side, you get y over negative 2. Y over negative 2 is not equal to 0 over 0. So beware, be careful. You can't do that to find out it and say it must be differentiable when x is 0. You're not allowed to cancel top and bottom like that when you're getting rid of a 0 over 0. So the answer to this is it's not differentiable when x equals 0 or x equals 2. And anyway. All right, let me get to the next theorem. Next theorem is kind of the backwards one, but it's helpful. So if x is a function such that the partial derivative of f with respect to x and the partial derivative of f with respect to y are both continuous at a point, then f is differentiable. Okay, so this is a very nice theorem. So it says that it's not good enough quite to say that derivatives exist, the partial derivatives exist, but if the partial derivatives are continuous, then we know we have a differential function. And that is a whole lot easier to show than this mess. Do you all agree that this doesn't look fun at all if we had to prove that to show it was differentiable? On the other hand, this theorem is actually a very nice theorem because finding a partial derivative and checking to see if it's continuous is not very hard. So this is a theorem that you're really going to be using to seeing if something is differentiable. Is you'll take the partial derivatives, and then when they're continuous, you know you get differentiability. Any questions on that? Any questions? Okay, it's not that hard to come up with examples. So for example, I don't know, f of xy equal x times y to the 1/3 So let's check to see when it's where this is differentiable. What's f sub x? You should all be able to tell me that. What's f sub x? This isn't supposed to be hard. Yeah, y to the 1/3. By the way, does that have any points of discontinuity? Are there any x comma y's where y to the 1/3 is not continuous? Yeah, there's no problem with y to the 1/3. So that is continuous everywhere. Now let's do f sub y. And that is equal to 1/3 x y to the negative 2/3. Does that have any points where it's not continuous? Or is that continuous everywhere? What can you tell me? So is that continuous everywhere, or does that have any issues? Help me out here. We don't have a lot of time. Jump on in. Okay, it's not continuous. When you have a negative exponent, you have a problem at 0. Because negative means bring it down to the denominator. So it is not continuous at y equals 0. Therefore, f is differentiable everywhere except at all points x comma 0. So if y is 0, it's not differentiable. Any questions on that? Okay, we don't have a lot of time, but I'm going to mention I have one last little thing to talk about. It's no big deal. And that is, if f is differentiable at a point, then let's let dx equal delta x and dy equals delta y. Then the total differential of f of xy at a point is dz equals, oops, forgot to put the dx, dy. F sub x of x naught y naught dx plus f sub y of x naught y naught dy. So it's just a definition. It's called the total differential. You've seen this with the differential in first quarter calculus, except then you just had f prime, or dy over dx times delta x or dx. So this is really the same thing, but it just adds on another variable. And you do the same thing with 3 variables. You just tag on another variable. There's not much to say about it. You just plug in. Any questions on that idea? Any questions? Okay, notice, by the way, this piece, we go towards the beginning, is basically the linear approximation without the z naught. So it's how much you're changing from your z naught. That's all that is. So we are out of time. So I'm going to stop the recording.